this equation you have so rate is equal to mass yeah, the gravitational constant. So this value is weird value.
Okay, this. Okay, so we have video hopefully and audio. Let me. Well, I don't know. Okay. Your turn. Which problems did you try? Which problems you want to see discussed here?
Number 17
From
chapter 4.
homework.
Yeah.
Problem 17 from chapter 4 homework. Oh, okay. So some problems I solved in class in section 1, other problems I solved in section 2. So if you have seen this problem, just be patient. And so problem 17 in the homework assignment is a direct application of Newton's law of gravitation, the universal law of gravitation, which says that the attractive force between two objects is the gravitational constant times the mass of one object times the mass of the second object divided by the distance between them squared. For our case, one of the objects is the planet Earth. Well, let me write it also this way. In this expression, objects that are close to the surface of the planet Earth are going to be subject to a gravitational force that is equal to, this expression is a constant for all objects that are close to the surface of the planet. Because in that case, R is going to be the radius of the planet. And M is the mass of the planet, and G is a fixed number. So the product of G times M divided by R squared is the acceleration due to gravity. So the gravity force can be calculated this way. Well, if you're far away from the surface of the planet, so if you have the situation described in this problem, so here is the Earth, and you're located somewhere here. So this is the radius of the planet Earth, but you have some additional distance right here, h. For geostationary satellites, h is the number given in the problem, 3.59 times 10 to the 7. And in this case, the acceleration due to gravity, g prime, is going to be again a product of the gravitational constant, which is listed in the textbook, times the mass of the planet Earth, which again is listed in the textbook somewhere or in Google. But now the distance between the geostationary satellite and the center of the planet is going to be the radius of the planet plus that height. And you have to calculate it this way. And now just plug in the numbers and you're going to get some number for the acceleration due to gravity. And that number is going to be smaller than 9.8.
So do we need to look up the radius of the Earth?
So when a problem like this is given in the test, those numbers have to be provided for the classroom.
Yeah.
So if I forget to write those numbers in the problem, you have to ask and I'll write them on the board. Okay?
So for this, because it's 17 and it's the homework class. We look up the radius for the
Oh,
Earth.
absolutely. For this homework problem, you have to look up the numbers. And I probably can solve it without looking at the numbers, but it is simpler this way, and I don't want to confuse people. Yes.
How did you rearrange that top equation to make acceleration equal g times? M?
Well, look, this is a product of this and this divided by this, right? This is this expression. And all those numbers are fixed numbers. When you calculate them, you're going to get exactly 9.8. And the dimension of that expression in the box, the dimension is a dimension of acceleration. So if you can try it, just look up the values of each of those constants, do the multiplication and division, and you're going to get a number that is very close to 9.8.
For that problem, that big mass that we'd use if we'd use the mass of the Earth
Yes, this is the mass of the Earth, yes.
in kilograms.
In kilograms. Everything has to be in SI units, kilograms, meters. Okay. Other? From the homework, right? Okay. So problem 18 from the same homework assignment. A space traveler with certain weight. And that weight is given in newtons rather than in pounds or any other units, which is the SI system of units, newtons for force. What will the traveler weigh in another planet with radius that is 3 times that of Earth, and the mass of that other planet is twice that of Earth? Well, look, it is very similar story. It is very similar story. So I'm just going to. Okay, let's write it again to use different letters, maybe. So in this problem, problem 18, you are told that on Earth you have certain weight, and that weight you can calculate. That weight you can calculate as a gravitational constant multiplied by the mass of the planet Earth and divided by the radius, capital R, of the planet Earth, and all of this multiplied by the mass of the person, the traveler. And when you do this calculation, they say that you get 630 newtons for the weight of that person. Yes.
Could you
bypass the equation and just multiply it by 2 nights, which is.
Yeah, this is eventually, something like this is eventually going to happen, but you have to justify it. Because if I give a problem like this, I can modify it and say the radius of the planet is 17 times larger and the mass is whatever. I can vary the numbers, and you have to see how you get the result for arbitrary numbers, right? So basically, now the weight in this different planet is going to be f prime, and it is going to be calculated by the same gravitational constant g, because capital G is universal constant of nature. But now you're going to have a different mass of the planet, m prime. You're going to have a different radius, r prime, which you have to square. But the mass of the traveler is the same. So they're asking, what is the value of this expression? And look, strictly speaking, you can use this first expression to find the mass of the person, substitute it in the second expression, triple the mass of this other planet, or whatever number they say, double the radius or whatever they say, and you're going to get a number that is going to work for WebAssembly. Alternatively, you can do the following arithmetic. You can divide this second equation to the first equation, and you're going to get cancellations, and it is going to be easier to handle it that way. So divide f prime to f. The result is going to be g times m prime divided by r prime squared, and all of this divided to g times the mass of the planet Earth divided by the radius of the planet Earth squared, and mass times mass here. And now the cancellations are going to be something like this. The mass of the person cancels out. The gravitational constant, Newton's gravitational constant cancels out. And you have division of two fractions, and that division of two fractions you can say is m prime divided by m, and it is going to give you r squared divided by r prime squared, like this. For my problem, they say that m prime is, what do they say for m prime? Mass is twice. So m prime divided by m is 2 for my version. So that this ratio of radii, I can write it like this, radii squared. And they say that the radius is 3 times. So this is 3 times larger. So this is 3 times larger than this. So I'm going to have, this is going to be 1/3 squared, right? And therefore I have 2 divided by 3 squared, 2/9. So f prime divided by f is 2/9. Therefore, f prime itself is equal to f times 2/9. In other words, it is 630 multiplied by 2/9. And this is how you handle it. But again, this is a short way to get the same number. Alternative way would be just first to find the mass of the traveler, plug it in here, double the mass of Earth or triple the radius or whatever they say, and you're going to get the same number.
Can you show how to find the mass of the traveler?
Right here. That mass of the traveler is also 9.8 times 10. Therefore, his mass is 630 divided by 9.8. But about 65 kilograms or so, 64 kilograms. Okay.
Actually, a question on the test, when you have like the word response kind of questions, are you wanting us to like plug in the numbers and then solve for the problem? Or you want to do that when we have like the variables and plug in the numbers at least?
So for the second part of the test, like in the practice test, where you have to show your work, you have to try to work analytically with formulas, and at the very end, you can substitute the numbers and see and get some number. And I'll instruct the graders if they see analytical solution formula to look at it rather than the numbers. So always prefer for part one where you have multiple choice, you can do whatever you want. But if you show some work, you may get some credit, extra credit.
14 of homework 3.
Of homework 3. Okay. Let's see any other questions before I go. Let's see homework. Look, 19 is right on the screen right now. Let me do it first, and then we'll go. Remind me, please. So 19 is elevator. This is a parent weight problem. We get something similar in one of the sections of the class, but let's do it now slowly. And so they give the mass of the person. Part A, the elevator is accelerating upward. So look, the statement accelerating upward doesn't mean that it's moving upward. It may be moving downward. The question, so the direction of motion and the direction of acceleration are not directly related. You shouldn't think that the motion is in any particular direction. So, and this matters in trick questions that I think that I put in the practice test if I didn't forget.
So does this just mean that acceleration will be positive? Is there saying accelerating?
So positive or negative, you don't know before you choose the direction of the positive direction of the coordinate system. When you choose it, then you can say it is positive or negative. You can make it either positive or negative. But let's see. So now the elevator, together with the person, of course, is accelerating. The acceleration points upward. So here is the floor of the elevator. Here is the person, and we always make the people smile. And what direction of coordinate system should we choose? Positive direction. Up, down, it doesn't matter. Okay, if you choose the positive direction to be up, they say the acceleration points up in part A, right? Up, and the acceleration in that case is going to be positive, for my version, positive 1.4. 1.4 meters per second squared for my version. Now, free body diagram. You have the weight of the person mg in downward direction. So the algebraic sign is taken into account when I draw the arrow. You don't need to insert negative g or anything. And the normal force has to be perpendicular to the floor, this way. The apparent weight of the person is the normal force. This is the force with which the floor pushes your feet, and this is what you feel as weight. So the net force that acts on this person is the normal force in positive direction. I'm taking it with positive sign, and the gravity force in negative direction. Here is the negative algebraic sign for the. This is the net force. And Newton's second law says net force is equal to the mass of the person times his acceleration, where the acceleration is positive 1.4 for my version. And from here you have to solve this for the normal force, and this is your apparent weight. So from here you say the normal force is equal to ma plus mg. In other words, this term goes to the other side of the equation with opposite algebraic sign, and that's it. So if you want to type less on the keyboard of your calculator, you have this. A is a positive number, G is positive 9.8. You're going to get the weight of the person is going to be larger than his real weight. The apparent weight is going to be larger than his real weight. Part B, when the elevator is moving up with constant speed. If the speed is constant, the acceleration is going to be 0, and therefore everything works, but his apparent weight is going to be his real weight, mg, right? This is going to become 0, and you have this. Yeah.
mg, is it just like his weight times gravity?
Yeah.
Okay.
Yeah. His mass multiplied by the acceleration due to gravity, 9.8, right? This is, don't mix up weight and mass. Those are different animals, even though in everyday life we think about them the same way. And part C, now the acceleration is down. And it has, if the acceleration is down in this coordinate system, it is going to be equal to negative 1.4 meters per second. And therefore, this is going to be negative 1.4, and the apparent weight is going to come less than his real weight. So, yeah.
So it says a 95 kilogram person, so are they saying that's their mass or their weight?
So so if it is kilograms, it is mass. The weight has to be expressed in newtons in SI system of units. So it is his real weight is 95 multiplied by 9.8, approximately 640, let's say.
If the mass was in grams, we have to convert it.
You always convert into kilograms, otherwise you're going to make a mistake of a factor of 1,000. Okay, other questions? So again, the inside system the basic unit for mass is kilogram rather than gram. Okay. Other? Yes.
I know, you need to go chapter, but can you also help with question number 21
From
from chapter 4?
Okay, let's finish what is on the screen because okay, here is chapter 20, problem 21. And again, this problem, I have selected this problem because some of you guys are hopefully going to go to dentistry at some point. And here they give you two forces that act on some tooth, I guess. And you have to find the net force. And it is not very difficult, but it requires you to realize that forces are vectors and you can decompose a vector into components. So you do this. So you do this. Here is maybe the tooth or whatever, the brace or whatever is in the diagram there. But you have the first force this way. This is 16 degrees, and you have the second force symmetrically. That's this way, with the same magnitude, again 16 degrees. And the magnitude of each of the forces is the same. T and T prime are the same in magnitude. So they say that T is the same in magnitude as T prime, and for my version it is 27 newtons. So look, what you do is you decompose each of those forces into horizontal and vertical components. So if you use some coordinate system that, let's say, is like this, x direction positive to the right, y direction downward, just for variety. Here is the composition of the force T. This is Tx, Ty. This is Ty. This is Tx. So instead of now working with this force T, I'm working with its components. And the same thing here. For T prime, here is T prime Y, and here is T prime X. T prime X right here. And what do you see? You see that the X components are exactly the same because the triangles that are formed are the same triangles with the same sizes, everything. So the X components cancel out. Well, the Y components are in the same direction and they add up. And you get that the net force F net is equal to 2 times the component, the Y component, right? And now from the diagram, you see, now this is 90-degree angle. You see that Ty, for example, is equal to the hypotenuse T multiplied by sine of 16 degrees. So this is the answer, 2 times 27 newtons times sine of 16 degrees. And you just have to plug in the numbers. Yeah.
Where did that net force equation come from?
So the net force is defined as the sum of the first plus the sum of the second You just have to add them as vectors. And the vector addition, you either add components or you do geometry. In our case, we kind of did something, components and geometry simultaneously. Kind of.
So since the t and t prime x, the tx and t prime x were the same and we canceled them, why did we not do that to ty?
Notice that tx points this way, tx prime points the other direction.
Okay,
So in opposite directions, they cancel out. While the y components point in the same direction, and you add them up. But this is why geometrical addition of vectors, you have to know it, right? Here it is, add x component and y component, and you get the total. And this is the rule for geometrical addition of vectors. This vector, tail to head rule that we started in the first week of classes. Okay. Other remarks here, any questions?
We just like solve that one out.
So I need a calculator and I don't have it because sine of 16 is going to be approximately 0.2, but again, I'm eyeballing it. So 0.2 times 2 is 0.4, 0.4 times 27 should give you somewhere around 12 or somewhere there. So if you want accurate numbers, help me with your calculator and we're going to get, yeah. Can you speak up a little bit?
Can we just do 22 on this page before we go back to chapter 3?
Yeah, but let's finish with this one. Okay, so if you plug in the numbers, we can check if, let's do it again. Say it again.
14 and 18.
Okay, so 14.8. We probably need one more significant.
Another 8.
Another 8, okay. So, well, there is no much. Yeah, that's good. Thank you. Okay. So let's finish with chapter 4, and then we will continue with chapter 3 and practice test and everywhere until we finish all the questions. Which question is next from chapter 4?
22.
Oh, this is a good and tricky one. But again, it is again a medical type of question. Yeah, that's a good question. Actually, I can formulate it in a way to make it more, I don't know, easy or more difficult or more meaningful. So you have crutches there, and they show the angle between the crutch and the vertical. And they're only giving you the coefficient of friction between the crutch and the ground. And they want you to figure out how much you can lean this crutch before it starts sliding. So it looks like they don't give enough information. But they probably do. Let's see. So here is the crutch. Here is the vertical. Here is the ground. And here is the force with which the ground acts. Yeah, this is a force with which the ground acts on the crutch. So that force has to be along the direction of the crutch. It cannot be in any other direction. Right? And this is a force due to the contact between the crutch and the ground. And we said in class that when you have contact between two objects, two forces are going to appear. One of them is normal force, perpendicular to the surface, and the other force is going to be friction force parallel to the surface. Well, this means that if you decompose this force into components that is perpendicular to the surface and a component that is parallel to the surface in some coordinate system, let's say like this, positive. Let's work with positive numbers. So let's choose those directions as positive. This force, how do you identify this force? Normal. How do you identify this force? Friction force. And it is static because you don't want the stuff to move. So call this angle, they call it theta. And now, since Fx is friction, static friction, the maximum value of the static friction force is coefficient of friction, static friction, times normal force. In my case, coefficient of friction, the normal force we said is Fy, right? This is the normal force. The angle, so the maximum angle is going to correspond to the maximum value of the friction force. And you can say also that tangent of this angle that you're looking for is going to be, by definition, tangent of an angle is opposite divided by adjacent side. So it is Fx divided by adjacent, Fy, and we're talking about the maximum value of the force and the angle. In other words, Fx maximum is coefficient of static friction times the normal force. The normal force is Fy, it cancels out. So we got that the tangent of the maximum angle is exactly equal to the coefficient of static friction. And therefore, the maximum angle, theta, is inverse tangent of the coefficient of static friction. Yeah, this is an elegant problem.
Will we have problems like that on the test?
I have, you know what?
No problem.
I probably will write the problem, the different versions of the test on the night before the test. So I don't know what problem is going to be there, but I can change the way I ask a question like this so that I don't know, it to be more. Because everybody can memorize the answer, but the reasoning is what matters here. But this is elegant problem. I may ask you, I don't know, I can ask you something like, what is the nature of the force F? Force F is a vector sum of normal and static friction force, or something like this. So problems of this type are good problems for standardized tests because they are simple. They don't need a calculator even, right? Because I can adjust the numbers in such a way to be able to find inverse tangent without calculations. Okay, other. So look, we're preparing now for the midterm and solving homework problems, but we're going to have at some point where we have to start also getting together with people that are planning to take standardized tests like MCAT and GRE. And so keep preparing your questions for meetings of that with that goal. Yeah. Okay. Questions, remarks? Okay. So are we done with homework 4? Okay, let's do what was the question from homework 3? Which question was it?
Problem 14.
Okay, let's see problem 14 from homework 3. Didn't we solve this problem in class in both sections? I remember solving this problem in one section, but I don't remember if I did it in the second. We didn't? Okay, let's do it then. Yeah, let's do it. Problem 14, homework 3. So you have a rifle, you have the target is at a distance A, at some distance, and it hits you, of course. So let's look at this following way. Here is the rifle, and here it is completely horizontal, and here is the bull's eye right here, and in the first case, the real trajectory of the bullet is going to be something like this. So this is when, so let's introduce a coordinate system like this. Positive X direction, positive Y direction. I'll choose it down to avoid minus signs, but you can choose it anyway. Origin of the coordinate system at the rifle. And they say that this distance is some number called HA. Now you increase the distance to the target. So this distance, call this distance X. And you increase the distance to the target, so you place the target right here. And in that case, the same bullet is going to go this way. And you are going to have a distance HB. This, and actually this distance now is, what do they say, 4.5 times. So this is a different distance, x prime equal to 4.5 times the original, the first distance. Okay, they want us to find the ratio of HB to HA. And look, what I'm going to do is I'm going to solve for the vertical components, maybe we'll see. I'm going to solve first for the motion of the first shot. And let's start with the vertical components of the first shot. So the vertical components of the first shot, initial velocity vertical component is 0. The bullet has 0 vertical component initially. Acceleration due to gravity is in this coordinate system is positive 9.8. Vertical displacement in this coordinate system is plus some unknown number, but I'll think that it is kind of known number. So if I think that this is a known number, from here I can determine the time of flight for the first shot. And I'm going to say, okay, let's find the time of flight for the first shot. So I need a formula that connects those variables. In other words, I need a formula that doesn't have final velocity. The velocity of the bullet when it hits, nobody cares about it. Formula that doesn't have final velocity probably looks like this. Y is V naught YT plus 1/2 squared, acceleration times squared, right? This is the formula. For our case, Y is equal to HA. V naught Y is 0, so this term goes away. And I have this is equal to 1/2 positive G squared . Okay, so this is good. What to write? So I expressed now the time is unknown here still. Now, I just will leave it this way, and we'll deal now with the x component again of the first shot. In x direction, the acceleration is 0, and the velocity of the bullet is going to be unchanged. And therefore, all the formulas that we have for kinematics are going to work perfectly fine. But the formula that I want to use probably is, let's say, the third formula saying that x is equal to V naught xt plus 1/2 axt squared. Well, I'm writing it, but most of the terms here are 0 because the acceleration in x direction is 0. This term goes away. And you have that distance is speed multiplied by time, something that nobody can argue with for motion with constant velocity. From this, so what is left is this. And I can say here that time is equal to distance divided by the launch velocity, which is x component or some unknown velocity. I can substitute this expression here, and I'm going to have that HA is going to be equal to 1/2 g, and instead of time squared, I'll write x squared divided by v naught squared. Do you buy that or not quite?
Why is it squared?
Because this is squared right here. T squared, so I substitute t, right, with x divided by v naught.
And how do we get v naught y equals 0?
They say that the rifle is pointed strictly horizontally. So when the bullet goes out of the barrel, it has only horizontal component of velocity. The vertical component initially is 0. But good to keep thinking about what it is like. Okay. Well, now repeat the same thing for the second shot. And you're going to get that the second shot HB is 1/2 g times the different distance squared divided by the same launch velocity, because you use the same cartridges, right? So you have the same initial velocity of the bullet. And now form the ratio that they want. So HB divided by HA is going to be 1/2 g x prime squared divided by g naught squared divided by 1/2 g x squared divided by g naught squared. And everything is going to cancel out. G naught squared with g naught squared. And you're going to get that this ratio is equal to x prime squared divided by x squared. In other words, it is going to be x prime divided by x, everything squared. This ratio, the problem says, for my version, it is 4.5. And that's, so this problem is put there to make you work with formulas rather than with numbers. If you try numbers, no numbers are given. So you cannot.
So on the test, will all those formulas from the kinematics?
The four kinematic formulas are going to be given to you. And any other formula, Newton's second law is going to be there. Friction equations, friction is coefficient of friction multiplied by normal force. If I forget to write something, you have to ask for it and I'll write it on the board.
So can we assume the formulas that are all listed on the practice test will be provided on the actual test?
Yes. Well, maybe some extra if I see that you need something extra. But again, don't stress out for the test. Just have to learn. Okay. Let's see any other questions.
Go back to,
Almost which? The form? Yeah. Which problem?
Figure 17.
Problem 17. Oh, we started with this problem, right?
Right, that's why you want to say it, because
Okay, so in this problem, you're practically asked to understand what acceleration due to gravity is. So the gravitational force is the constant, Newton's gravitational constant, times the mass of the first object times the mass of the second object, divided by the distance between them squared. When the object is on the surface of the planet Earth, m is the mass of the planet Earth. The distance between any object and the center of the planet Earth is approximately equal to the radius of the planet Earth. And in that case, this combination of constants, when you do the multiplication and division, you're going to get exactly 9.8 times m. So acceleration due to gravity is just gravitational constant times the mass of the planet times the distance between the center of the planet and the object. For a satellite that is very high above the surface, here is the planet Earth, is the center of the planet Earth. Here is the satellite somewhere here. They say that this distance is the number that they give, and this is the radius of the planet. So the acceleration of an object that is located at the place the satellite is going to be G prime is going to be gravitational constant times the mass of the planet Earth divided by the radius of the planet Earth plus this additional height h, everything squared. And now you have to look up the numbers for the mass of the planet Earth in kilograms, the gravitational constant, and the radius of the planet Earth in meters. And calculate this, and you're going to get some number that is going to be smaller than 9.8 meters per second squared. So again, this problem is to draw your attention to our definition for acceleration due to gravity. Okay, let's see other questions. Or maybe anything related with this. Yes,
Can we go over question 11?
from homework 3. Question 11 from homework 3. This one, right? Oh, this is 12. Oh. Okay, so you have to look at this conceptual example. And now, so the first case, the plane is flying in direction above the horizontal, and when it releases this fuel tank, it is going to, this fuel tank is going to fly initially upward. So initial velocity of the fuel tank is going to be V naught, is the horizontal, and this angle is going to be 15 degrees. 15 degrees, like this, right? Now the trajectory of this fuel tank is like this. It will keep going up and eventually it's going to fall like this, right? They're asking us in part A to figure out the magnitude and direction of the final velocity of this fuel tank when it hits the ground. So when it hits the ground, here is the final velocity vector. And like always, you start by decomposition of all the vectors given and the vectors that you're looking for. Coordinate system, I would choose, to avoid minus signs, I would choose positive y direction to be. Well, okay, let's keep it in downward direction. So they say that the distance between the ground and the plane, for this version, that distance is 2,000 meters. So 2 kilometers is 2,000 meters. So this is 2,000 meters. Okay, now let's do the decomposition. This is the vertical component of initial velocity, v naught y. And it is equal to hypotenuse v naught, which is given, right? It is, for me, it is 130 meters per second. Multiplied by sine of 15 degrees. And now look, my choice of coordinate system, v naught y component is directed upward, but I have selected positive direction to be downward. Therefore, v naught y is a negative number, and I have to insert a negative algebraic sign just by looking at the diagram. In a similar manner, the x component of launch velocity v naught x is going to be equal to v naught times cosine of 15, this time positive. And now let's see what we know about. In a similar manner, we have to decompose the final velocity. The final velocity is going to be with y component this way and x component this way. Like always, the components are perpendicular to each other. Since they're asking for the final velocity vector, I have to find its components, and knowing the components, I can figure out the total final velocity. The x component of final velocity is exactly the same as the x component of initial velocity. Because in horizontal direction, no changes happen. So the issue now is to find the vertical component of final velocity. And I can formulate the questions related with the vertical components. So for the vertical components, I know the launch velocity is negative v naught times sine of 15. I know acceleration y component is positive 9.8 in this coordinate system. And I know that the vertical component of displacement is positive 2,000 meters, right? Because the displacement vector is right, this vector, and it has y component of 2,000 positive, and it has some x component that nobody cares in this problem, so I'm not going to. But for y component of the motion, I have my three numbers, and I can determine everything. What is interesting is y component of final velocity. In other words, I need a formula that doesn't include time. the time of motion. And the formula that doesn't include the time of motion is the fourth formula in our list. So it looks like this. Final velocity y component squared is equal to initial velocity y component squared plus 2 times acceleration y component multiplied by displacement x component. And well, here everything is given. I just have to calculate it. So this is going to be something like v naught times sine of 15 degree. There is a minus sign there, but this has to be squared plus 2 times g times 2000. In other words, I can calculate this number if I want. Because we notice 130, the minus sign is going to disappear when I square. And now, looking at the triangle that is formed by the components of final velocity, I can say that the final velocity which the problem is asking for is from the Pythagorean theorem, the x component squared plus the y component squared. And that's it. So this is square root of x component squared of final velocity is v naught cosine of 15 degree squared. And vy is the expression that we just calculated. Well, I don't want to copy it. It is just vy squared. And you add them and you're going to get some number. So this is the first part here. The magnitude of velocity is found. How to find the angle between the final velocity and the horizontal, this angle. How to find that angle? Well, look at the right triangle that is formed by the components of the final velocity. Call that angle alpha. And from that triangle, you see the tangent of that unknown angle alpha is opposite side, which is vy, divided by, which is vx. No, it is vy, opposite to the angle is this. So it is vy divided by adjacent side, which is vx. So, I'm sorry, there is no subscript y here, right? They're asking for the total velocity, not for, and this is the total velocity, Pythagorean theorem. But vy is calculated, actually its square is calculated. But you can take square root and have vy. Vx is also known. So the ratio is the tangent of the angle. And therefore, the angle itself is the inverse tangent of that expression. So it is a problem that kind of, it is not that complicated. Part A is this situation. So you have to think about it, and you have to try to do it independently, and you're going to see that it makes sense in general. Now, part B of this problem is directly the conceptual example that they quote. Basically, they are telling you, so if you, here is when you launch this fuel tank in upward direction, and this is the horizontal, and when this horizontal intersects the trajectory, the velocity of this fuel tank would be like this. This is the velocity vector. And the symmetry of projectile motion tells you that well, this angle between the velocity vector and the horizontal is going to be again 15 degrees. This is from the properties of the projectile motion, right? This component of the velocity is going to be the same as the launch, but in opposite direction. The other component is going to be the same. And therefore, those two triangles are identical triangles. And therefore, this angle is 15 degrees. And look, it is as if you have launched this fuel tank at this point with in direction of 15 degrees, but below, exactly part B. And therefore, well, if this is the launch, it's just going to continue the way it was moving in the first case. And it is going to hit the ground with the same final velocity directed at the same angle as part A. So conceptual example, read it and make sense of it. And you see that it solves the problem. Let's see questions and remarks.
So the negative V no sine 15 for the V naught Y, you chose for that.
Yeah, it is a positive number in this coordinate system, but nobody is asking about it, right? So in this coordinate system, this is a positive direction. So this is a positive component of velocity here, and also here also positive number. So the negative number appears right here. This is a negative velocity here. I inserted a negative algebraic sign, but eventually it cancels out because I'm squaring it.
Because you decided to make that negative, then the acceleration of Y is going to be positive as well.
Yes, and the acceleration it is positive. In this, because acceleration due to gravity is this way, and this is a positive direction for me. So here I took it positive. Okay, let's see other questions and remarks. Yeah. Number 13 on homework 3. Okay, so you launch a projectile and you see the trajectory and you see the range. If you launch, okay. What is good here is that you have a good diagram here. Here is the launch velocity, tangential to the trajectory, launch angle, components of the launch velocity are shown. I usually draw the vertical component here, but it doesn't matter where you draw it. It is a very good diagram. And look, I can cheat a little bit and tell you that we solved a similar problem in the very first day where we discussed chapter 3. In other words, it was the first class on chapter 3, and it was a situation like this. Here is the trajectory, and here is the launch velocity V naught, and the launch angle was angle theta, and the range is this distance. We use the coordinate system like this, x and y direction. In this coordinate system, we calculated this range of motion. We did the arithmetic by analyzing x components, y components separately. And actually, we did it in two different ways in different sections. But the result was like this. The range, the horizontal displacement came out to be 2 times initial velocity squared times sine of the launch angle times cosine of the launch angle divided by 9.8. So we can derive it again, but just to save time, I'm writing it. And you actually are not allowed in the test to take this formula as granted. You should, if you have to use it, you have to derive it. Where is the real issue here? And now from this formula, you see that, what do they say? You keep the angle unchanged. You double the speed, but the angle stays unchanged. So if you double V naught, the range is going to quadruple. So it is going to become 88. If you triple, it is going to be multiplied by 9. So the range is going to be 88 for my question. Yeah, and this should work. But again, the real heavy labor was in derivation of this formula. Okay. Let's see other questions. Nobody is asking about the practice test. I'm puzzled by that. You didn't even have time to look at it. Right.
Last questions tomorrow.
Okay.
Or are we gonna be going over chapter 4 some more? I thought we finished that.
We're
Monday.
practically, I think that I can say a few more words about chapter 4, but we're almost done with chapter 4 discussion. I have some questions that I can add, but
So is it okay to ask questions about the?
oh, it is always okay to ask anything, anytime. So including including practice test. But again, the class time is 50 minutes. And then we have to go. I have other classes after that. But yeah, check the practice test questions independently. Try them at least for a few minutes. And those that are more difficult and you cannot handle them, bring them for class. And also, nobody also offered a problem that we to agree that problem to be on the real test, right? I gave you the opportunity you to write your own test, and you never took this opportunity until now. So maybe tomorrow is the last time. If you offer a problem that is not completely trivial, but also not very long, and it has some connection with real life, with your major, offer that problem. We're going to solve it in class, and we're going to declare that that problem is going to be on the test. Right? This is not that I'm lazy, but I'm giving you the opportunity to write the test for me. Not because of my laziness or any, just you to look at different problems and see maybe something that is useful for you. Okay, should we end it here or you have other questions?
420 or 423.
Okay, let's do problem number 20 from homework 4. So I think that I started working on this problem in class in one of the section, but okay, so let's look at it this way. Here is the incline. Here is the car, and that car is at rest. So you have incline is at an angle 15 degrees above the horizontal, like this, right? And like always, you start with a free body diagram showing all the forces that act on this car. So of course, you have the force of gravity is acting vertically down. And of course, the normal force is acting perpendicular to the surface. So this is the normal force. But again, if there is no friction, this car is going to be sliding. So there should be some friction, and the friction should be directed upward to cancel out, to prevent the sliding. This is static friction. Okay, and now part A, what is the normal force, the magnitude of the normal force? So use a coordinate system that is with one axis, x-axis, let's say, parallel to the incline, and the y-axis perpendicular to the incline. In this coordinate system, again, origin is at the center of the object. In this coordinate system, you decompose the weight into y components and x components, right? It is y and x components, something like this. So this is and now look, you formed the right triangle from the components of the weight. The hypotenuse of the right triangle is mg, but the x component, so what is this angle? This angle is 15 degrees because this angle has arms perpendicular to this angle. And there is a theorem in geometry which says that if you have two angles with mutually perpendicular arms, those two angles are equal. So indeed, the arms of this are perpendicular to the arms of this. And therefore, you have 15-degree angle. And therefore, the x component happens to be mg sine of 15 degrees. So notice here that the x component comes with a sine rather than cosine as we used to have. And similarly, the y component of the weight is mg cosine of 15 degrees. Strictly speaking, it is in negative direction in this coordinate system, but I just will work with magnitudes and I'll take into account the directions when I'm writing the equation. And now they say that the car is at rest. There are no other actually, the only forces that act in y direction are the normal force in positive y direction and this component of gravity in negative y direction. No other forces in y direction. Since the car is at rest, the car doesn't fly above the surface, doesn't sink below the surface. You must have the net force in y direction to be zero. In other words, F normal in positive direction and in negative direction is mg cosine of 15 degrees. They have to give zero net. And therefore, the normal force happens to be mg cosine of 15 degrees in magnitude. So this is part A. And part B, they're asking to figure out the static friction force in magnitude. Well, you do the same story. You say in x direction, the forces also have to total to zero. And in x direction, you have this component of gravity that is acting in positive x direction. So it is mg sine of 15 in positive x direction, and the static friction in negative x direction, and they have to add up to zero so that the car doesn't slide, and therefore you have the static friction force is mg sine of 15 degrees. So here is part A, here is part B. Again, notice that the entire solution of the problem is in the composition of the gravity force into component parallel to the surface of the incline and component perpendicular to the surface of the incline.
Why is it mg times sine or cosine?
Yeah, this is a good question. Let's see this one. So by definition, a sine of an angle is opposite side
Over hypotenuse.
divided by the hypotenuse. And the opposite side, call it, well, you have to call it something, but so hypotenuse is mg, and the opposite side, call it, well, I have to put a name to it, fx, let's say. And from here, the x component fx is mg sine of 15 degrees. And similarly for the cosine, by definition, the definition of cosine is adjacent divided by hypotenuse, and you can come up with this for the value of the force Fy in magnitude. Okay, other remarks here?
I'm sorry, can you explain again how you got mg sine 15 or sine of 15 degrees minus
So I'm looking at all forces that are present in x direction. So in x direction, I only have this in negative x direction, the friction. And I have this force also. It is a component of the gravity force that acts in that direction. Right? This is the no other forces in x direction. They say that the object is at rest, doesn't move, doesn't accelerate, doesn't do anything. Therefore, the forces have to cancel out. And I'm canceling out the x direction forces. If they don't cancel out, right? If this and this are not equal to each other, this car is going to start sliding or going upward. Well, cannot, right? It is just from the condition the car to be at rest. The forces have to cancel out, right? You have Fx net force in x direction is equal to mass times acceleration. The acceleration of the car is 0 because they say it stays at rest. And therefore, Fx net has to be 0. Here it is 0, and this is the net force. The sum of this one happens to be negative, but
So is static force always net force, or is it?
this is one of the two forces in x direction in this problem.
Okay.
So the static friction opposes the sliding. So this is why I drew it this way to oppose the sliding. And this component of gravity wants to slide the car. So it is in my coordinate system, it is in positive direction. This component right here, you can think about it this way. Right? It is the same force, no matter where you draw it. We're working with free vectors. We draw them wherever is convenient for us. Okay. So again, when I'm solving a problem on the board, it seems easy and you understand everything. When you sit down to do it independently, you're going to discover things that you haven't seen when I'm doing it. So try independently more than once for problems that need more attention. Okay, let's see any other issues, problems, questions.
Sure.
23.
Oh, you said 23 and I forgot.
That's okay.
Yeah, well, don't forget, like I did during the test. Right? Oh, this different type of problems. Why nobody asked so far? Good. Problem 23 from the homework on chapter 4. So you have two blocks connected with a string. And luckily for us, they say no friction anywhere. You want to figure out the acceleration and the tension in the core. Yeah, this is a problem that. So here's the block with mass. Oh, they don't even give the masses; they give the weights. but call the mass of this first block M1. And here's the pulley, and everything is hanging. Here's the mass M2. And you can find the masses by saying that the weight of the first is M1 times G. So the mass of the first one is M1 is the weight that they give divided by G, and similarly for the mass of the second. M2 is the weight of the second divided again by G. So those are known. I'll erase here because this interferes with my diagram, but you have the masses. And now you have to draw free body diagrams for each of the objects. So forces that act on each of the objects. And here you need two coordinate systems, but they have to be consistent with each other. So the coordinate system, maybe for the first object, you choose it this way. Ups, no. Which way to choose it? Okay, this one can stay this way. But for the other, you have to take it consistent in such a way that when this one moves in positive direction, the other one also to move in positive direction. So something like this. And the second mass doesn't move in horizontal direction, so I don't care about that. But what matters is this direction positive to give you positive here too, not to get confused by the arithmetic. And now let's draw the free body diagram for the second object first. The second object only is going to feel the gravity, but the string is going to pull it in upward direction with tension force T, like this. Right? The string is slowing it down. For the other mass, you have the weight, you have the normal force, and the string is going to pull it this way. The action-reaction law guarantees that this tension force is equal to this tension force in magnitude. Action-reaction. They are not in opposite direction because the string shifts the directions appropriately, but the magnitudes of the forces are the same. So you can use the same letter to denote that. Also, for the force acting on the first object in vertical direction, well, in vertical direction, this object doesn't move in vertical direction at all. Right? It doesn't go above the surface, it doesn't go below the surface. Therefore, those two forces cancel out. And the net force that acts on the first object is just the tension force T. And you can write Newton's second law for the first object. It is going to read like this. The net force acting on the first object, just the force T, is equal to the mass of the first object multiplied by its acceleration. Now we have two unknowns, the acceleration and the tension force, so you cannot solve it. But you go and you write Newton's second law for the second object. So for the second object, you have mg in positive direction, and tension is acting in negative direction. So this is the net force acting on the second object. It should be equal to the mass of the second object multiplied by the acceleration of the second object. Well, the two blocks are connected with a string and they move together. Their acceleration is the same, so I'm using the same letter for acceleration. They just move together. And now I have two equations with two unknowns, and I can find the acceleration and the tension force. So you can solve the system of two equations any way you want. Probably you can substitute t from the first equation in the second equation, and you're going to get something like this: mg minus m1. This is m2, right? M2. M2g minus m1a is equal to m2a. And in this equation, the only unknown is the acceleration. You bring the terms that contain that unknown to one side of the equation. So this goes to the other side of the equation with opposite algebraic sign, and you get something like this. M2g is equal to M2a plus M1a. In other words, you get M2g is equal to, you can factor out a, in the brackets you're going to have M2 plus M1, and factor out a. And now solving for the acceleration, you get acceleration is equal to M2g divided by M1 plus M2. So this is the acceleration. Once you have the acceleration, take it, plug it in here, and you get the tension. So again, a substantial part of the solution was the diagram, which coordinate system and three-body diagram for each of the problems, for each of the objects. See questions?
Where did you get the m2g minus t equals m2a? What equation?
Newton's second law
Oh,
for this object. Net force is mass of that object times its acceleration. Other questions, Max? Okay, let's end it here because it became way too long. But I'm going to be around. When I'm not in class, I'll be in the office. I'll try to be in the office most of the time. And we can also work in class. So